MOSFETs are popularly called as MOS transistors. Now, MOSFETs have many advantages, as we have talked earlier. They take fewer steps for construction, they take much lesser space, they have very high input impedance, thus they consume very low powers. Besides that, there are certain other points which go in favor of MOSFETs, and these other factors are that MOSFETs can be connected, we have seen, as amplifiers, as switches of course, but besides that they can be connected as resistors and capacitors also. Now, you may say that in a circuit, if the purpose is served just by connecting a resistance, then what is the necessity of replacing it by a MOS transistor, for example? There is an advantage. When we connect a resistance, for example, in a circuit like this, here this is the resistance connected, and when the current flows through this resistance, there is a dissipation of power, the normal I square R, the heating of a resistance, that is a shear dissipation of energy. Now, if this transistor can be replaced by another transistor, for example, we are at the moment talking of MOSFETs. So, if this is replaced by a MOSFET, then also as a resistance, then also the circuit will work and it will be power wise more efficient than this resistive load. When a circuit makes use of a resistance as a load, this is called passive load. Passive load, the resistance which consumes power proportional to R, the value of load which we are using. This is a passive load. Active load, when resistor is replaced by an active device which acts as a resistor, then this is called active load. So, besides power saving, there is additional advantage, because today very large number of circuits are actually in integrated circuit form. In integrated circuits, remember one thing, that creating one, for example, in a unit, one MOSFET and one resistance is more expensive and it will take more steps for fabrication than two resistors. That means, if we can replace this resistance by a MOSFET, then the circuit will make two MOSFETs, but making of two MOSFETs, or in fact just multiplying in some component, is much more economical and convenient in a integrated circuit rather than creating a different element altogether. Resistance and MOSFET, two are very different elements, and two MOSFETs, they are they belong to the same category, and hence their construction is very simple and more economical. So, now we start that how a MOSFET, a MOS, can be connected as a resistor and as a capacitor. So, MOS as MOS, which is same as MOSFETs, as resistors and capacitors First we take how a MOSFET can be connected as a resistor. So, MOSFET as a resistor. Let us, one of the ways a MOSFET can be connected to work as a resistor is this. This is a MOSFET in which we have connected, this is gate, this is a drain, and this is source. The gate has been shorted internally to the drain. In this, the E MOSFET, that means enhancement MOSFET, works as a resistance, as a resistor, because now we will show this point, because here since we have shorted the gate with the drain, then this voltage VDS between drain and source is same as VGS. This is shorted and this is VGS. So, this is same as this voltage VDS. VDS is equal to VGS, and the condition we remember that drain and VDS, the condition here, so that this MOSFET works in the saturation region, that condition is that VDS is equal or greater than VGS minus VT. If this condition is satisfied, then this MOSFET, when connected this way with other parts of the circuit, of course, then it will work as a resistor, and it will work as a in the saturation region of the characteristics, and we will show that this will work as a resistor. Now, if VDS is equal to VGS, if VDS is equal to VGS, then for all voltages above VT, the threshold voltage is around 2 volts normally. So, if VGS is equal to 2 volts, then in this condition VDS will be 0, and if VDS 0 implies 0 drain current is 0. So, if we make a plot of this point, that different values of VDS are equal to VGS, then we get a plot like this. VDS in volts and drain current in microamperes, and here it is 200 microampere, here it is as typical values 100 microampere and so on. Then the plot, as we have talked here, when what is the loci of these points where VDS is equal to VGS, and we have seen that when VGS is 2 volts, then VDS will be 0 and ID will be 0, and that point will start from here, and then 4, 6, 8 and so on. So, here this is the loci of the points. Here this is loci of points VDS, this is VGS, VDS is equal to VGS. This is output voltage, and this is of course drain current, and this slope of this curve, this dotted curve, that will give the resistance. This will the resistance, which is of course varying because the slope of this curve is varying. So, dotted plot gives the variable resistance of the device when the device is connected in this fashion. And we can see here that this resistance of course is a non-linear resistance, and because normally we work in this region, so there any value depending on the type of MOSFET which we are using, we can choose. So, we can see that this acts as a resistance, and we can calculate that value, and let VDS equal to VGS, which is true for all these points, equal to V. Then in this saturated region, the drain current, which is I, it varies as K, it is the VGS, which is now V minus VT square. This is for voltages greater than VT. By solving this, we can get the ratio V by I, V by I ratio, which gives the DC resistance, and this comes out to be 1 by Ki plus Vt by I. So, this is the value of resistance. This is true for voltages greater than Vt, and when we differentiate, this is DC resistance which this device will give, and by differentiating it we can get the AC resistance, and that comes out to be R AC by differentiating this equation, and this comes out to be 1 by root K I, where K is the device constant. This we have discussed when we were discussing the enhancement MOSFET. So, this is the value of AC resistance, and this is also true for V greater than Vt. So, this way the resistances can be calculated, and for the device we know what is the K and what are these drain characteristics. From there we can find the value. This was how a enhancement MOSFET can be connected as a resistor. Similarly, a depletion MOSFET, normally the most commonly used symbol for depletion MOSFET which is written as depletion DMOS. DMOS. The most commonly used symbol for DMOS is this. This is drain, source and gate. This is DMOS symbol, very commonly used, and this gap is the difference with the JFET. In junction field effector, junction field effect transistor, this gap is absent. So, this gap is. Now, this MOSFET can be connected like this. This is source, this is gate and this is drain. When we connect like this, then obviously VGS is 0. This is VGS is 0 because both have been shorted, and on the drain characteristics, this is VDS and this is ID and this is VGS equal to 0. Here it goes negative values, VGS equal to, for example, minus 2 volts. Here this is VGS equal to plus 2 volts, because a depletion MOSFET can be used as an enhancement MOSFET, as a depletion MOSFET and so on. This we have talked. So, in under this condition, this represents the slope of this one, VGS equal to 0. Now, this slope, this is very high resistance, this is almost flat, this is the voltage, this is the current, and so this slope, inverse of this slope, voltage by current, that represents the resistance, is a very high resistance. So, a DMOS can be connected like this by shorting gate with the source as a resistor, and then how the circuits will look. The circuits with active load will look like this. This is the E MOSFET connected as load, and this is, for example, say a amplifier. So, these two transistor T1 and T2, they give the complete active load and amplifier circuit. So, this is a MOS amplifier. In the same way, we can connect a depletion MOSFET instead of E MOSFET. This is E MOSFET, EMOS, this is the DMOS. this is DMOS as load, and this is the EMOS for as amplifier. We get output here, input is given at this gate of T1 and this is T2. So, input is given here and output is taken here. This is another MOS amplifier with EMOS acting as amplifier and depletion MOSFET DMOS as load. So, these are the amplifiers, they can be analyzed and completely satisfactory performance can be obtained. So, this is how that a MOS transistor can be connected as a resistor. So, such circuits on a chip will contain only MOS circuits properly connected. Then we take MOS capacitor. We will recall the structure of EMOS. Let us look at EMOS, and the EMOS structure was like this. This is P silicon, this is N heavily doped N, one is drain, the other is source, and this was the SiO2 layer, and over that there is a metal. Here also there is metal, this is also metal, and then this is gate, source, and this is drain. Now, here this is the channel. So, this structure is known to you. Now, this forms the metal at the gate, metal, and then insulating SiO2, and then here this is also having conductivity, much higher conductivity as compared to the SiO2 layer. So, this is another, this is semiconductor actually at the back. So, this is a MOS capacitor, metal oxide semiconductor. Now, so this capacitor can be used as a capacitance, and this gate capacitance can be, because there are overlap regions with the source and drain. So, the gate source GS, gate source capacitance plus the total gate capacitance can be shown as consisting of three terms: the gate source voltage, the gate and drain CGS, CGD plus CGB body, this body, this acts as a, so the total gate capacitance that contains three terms because of the overlap of the gate region with the source and drain. So, this is equal to WLCOX, where W and L are channel width and length, and this COX, this is equal to epsilon 0 epsilon oxide layer dielectric constant and thickness of the layer, where this is the dielectric constant of the SiO2, and which is around 3.9, and this is the permittivity of free space, and this is the thickness, oxide layer thickness, oxide layer thickness. So, this is one way the capacitor can be realized. In another form of the capacitor, the drain and source, they are shorted, and CGS acts, works as the required capacitor. This is another way. One way as capacitor was shown here, where the total gate capacitance contained 3 terms, 1, 2, 3, and another way is when drain source are shorted together and the capacitance between gate and source is used. And the third possibility is that, for example, if the one side of this capacitor is grounded, for example, the body side here, this is the layer, oxide layer, and here, and this is the body which is a semiconductor, this is grounded, then we can directly use CGB, B for body, this. So, this is the another way. Very often the MOS devices are connected as capacitors. Here there is no need to create a source and drain, they are absent, they are not required. So, this way the capacitor CGB is quite popular, and very often the devices are connected like that. So, this is how the 3 ways a capacitance can be obtained, a capacitor can be formed by a MOS device. So, the circuits will contain purely MOS devices. Some will be connected as amplifiers, others will be connected as active loads, and still others may be connected as capacitors. So, that it is all the MOS network in which different MOS are working as either as amplifier or as capacitor or as active load. Now, we go for another kind of MOS circuits which are very popular, and these are CMOS circuits. CMOS, C stands for complementary MOS, complementary MOS, CMOS. What is CMOS? Normally we have seen that we use either NMOS or PMOS, but CMOS is on the same chip. NMOS and PMOS are simultaneously present, they are connected. We will take example in which one circuit will be a PMOS, the other the one transistor will be PMOS, the other transistor will be NMOS. For example, we took these few examples of the circuits. They were connected, of course, in a resistance configuration. but otherwise one can be a PMOS, other can be NMOS for a CMOS circuit. This is a special connection where they were connected as resistors. Now, so remember that complementary MOS, CMOS, that contains on the same chip the PMOS and NMOS devices simultaneously. CMOS are very widely used in advanced circuits. They are most popular, and the reason for their popularity are these reasons for high popularity. All the advantages which most devices offer over BJT that we have talked. In addition to that, one advantage is least power consumption. Least power consumption. Till today, the lowest power consumption shown by exhibited by any logic is by CMOS. Least, we will see that why it is least. So, power dissipation, that means power consumption, is least in CMOS. This is one reason, and yet another reason for their popularity is faster switching. The speed with which they can switch from one state to another, high to low or low to high, this is very high. Now, we will take one device which is called the inverter. Inverter circuit. What is the inverter circuit? What is its function, and why I am taking it? Why it is so important that it should be taken first? Inverter means, first let us see the function. The function is a circuit in which low input results into high output. Low input results in high output, or high input similarly high input will result into low output. This is the inversion function. Voltages have been inverted. A low input results into high output, inverted from low to high, or high input from high to low output. So, that is the function of the inverter. Now, inverter is very fundamental for any digital circuit. Most fundamental for any digital circuit, circuits which work on two states, high and low, 0 and 1, false or true, whatever you may call, but actually electronic circuits understand the voltages, and so the voltages are low or high and the circuits respond to that, and all logics can be constructed based on these circuits. Now, for any digital circuit, inverter function is basic, and by combining inverters we can get, for example, if time permits, then we may also take these circuits, the two most fundamental and most important universal gates, the NOR gate and not NAND gate. Inverter circuit is also called NOT function or NOT gate, and by combining these inverters we can get a NOR logic or NAND logic. I repeat that inverter circuit, inverter function is basic to any digital circuit, and by extending the function of the inverter, by connecting inverters, we can get NOR function or a NAND function. Any logic can be realized, can be constructed in NOR logic. Two level NOR logic can result in any logic you can form, you can realize, or instead of NOR we can use NAND, and we can get what we call NAND logic. Two level logics are most popular, NAND logic, and similarly here NOR logic, NOR logic, NAND logic. So they are most important for any digital circuit, and to these NOR and NAND, inverter function is fundamental. So first we take a inverter function. Let us first, before moving to CMOS, let us take a inverter with a resistive load, and then later we replace that resistance with another transistor, and that will become CMOS. So inverter with resistive load. Load is the resistance across which we take the output, so it is called load resistor with the resistive load. So the simple circuit is this. This is the EMOS, and this is VDD, and this is the load resistor RL. This is drain, this is gate, and this is source, and output is taken here. From here we take V out with respect to ground. The input is given between gate and source. Source is of course grounded. This is the input, and output is taken here, and this is the EMOS, and this is the load. Now the output we are taking as V out, we are taking as between drain and source VDS. If a drain current ID flows through it, then at the output circuit we can write the Kirchhoff's voltage law at the output circuit, and that is simply summation of voltages. So VDD is equal to RL into ID plus VDS. This is VDS, same VDS, and here, or VDS is that is the output V0. From here itself this is VDD minus RL into ID. Now see how will it work. Case 1, when input is low, this Vi is low, that means it is 0. When this is 0, then obviously because Vi is also same as VGS, is same as VGS, and since it is 0, that means it is obviously less than Vt. This will require high voltage for its conduction, but in the present case input is low, that means VGS is less than Vt, no conduction channel will be formed, and ID, the drain current, will be 0. If drain current is 0 here, this term becomes equal to 0 and output becomes equal to VDD, which is normally will be 5 volts, that is high. Low input results into high output. This is what we expect from the inverter function. So this is case 1 when input was low. We take case 2. Case 2, when input is high, Vi is high and it is greater than the threshold voltage required for the channel formation in the device. So under this condition, this will conduct CMOS conducts, that means it is on. Earlier it was off, here this is on and current will flow, and in this equation now there is a current, a resistance, so there will be quite a bit voltage drop across this, and that voltage drop may be close to VDD itself, and therefore ID high and drop across RL will be RL into ID, which may be close to VDD. Therefore, from this equation which we wrote initially, this equation VDD or VDS, which is output, this was shown to be VDD minus RL ID, and since this is also equal, almost equal to that, so this will be close to 0, that means low. What we are getting in this circuit, which is a resistive load inverter, when input is low we are getting high output, and when case 2, when input is high, then we are getting low output close to 0. This is inverter function, and this was the conventional case, and now we can take the CMOS, the complementary MOS, in which we will replace this transistor also, this resistance also with the MOS of another kind. If it is NMOS, then it has to be PMOS, and as we said in the beginning that in the complementary MOS, the NMOS and PMOS transistors are simultaneously present on the same chip. So that will be the CMOS inverter. So we can take the objective, why we took this inverter, this is with the resistive load to tell you what is the function of the inverter and how it can be realized by a resistive load. Now we can move to CMOS inverter. CMOS inverter, in which the PMOS and NMOS transistors will be simultaneously present. So, here is the circuit. This is the circuit. This is NMOS, this is PMOS, and this is gate, this is gate, this is source, and note here that the source is here and this is drain. This is drain and this is also drain for NMOS. In this circuit, the NMOS acts as a driver. It will drive the PMOS. So, technically it is known as a driver, and PMOS is acting as load. We said that we are going to replace the resistive load with another kind of transistor. So, we have replaced that transistor with PMOS. So, PMOS will act as a load and NMOS will act as a driver, and input is formed by connecting both gates together. As it is clear from the figure, both gates have been connected together to form the input. So, input is taken from these combined gates with respect to ground, and similarly by connecting drains together, the output is taken with respect to ground. Now, we will see how this circuit works. First, let us note that PMOS requires, this is important, that PMOS requires a negative voltage at the drain. Instead of using two batteries, one for the NMOS and other for the PMOS, the same function can be obtained by connecting source to a positive voltage. I repeat what I have said, that PMOS requires a negative voltage minus VDD at the drain. Now, there are two ways it can be achieved. One is that we connect a negative VDD at the drain, or we connect a positive voltage source at the source. So, this is what the later scheme is followed in this figure, and so this is the way the the single DC source VDD is used to bias PMOS and NMOS. They can be. So, we will remember this circuit, which is the circuit for a CMOS inverter, and here some fundamental relations we have to realize, and these relations are, first let me write and then I will explain. Vi is VGSN and this is equal to VDD minus VSGP. This is equation number 1. This N, subscript N here, this is for NMOS, and this subscript P here is for PMOS. So, VGSN, this is the gate source voltage for the NMOS, and VSGP, this is the voltage between source and gate for PMOS. And then we can see here what we have written, that GSN, what is the gate source voltage for the NMOS? This is equal to VDD minus the voltage of VSGP for the PMOS. We will continue this function of the CMOS inverter, and then we will show that why the power consumption is least in this logic, and that is the reason that CMOS logic today is most advanced and very widely used logic.